phase of the equation states that we should attach a ball to each end of the string and connect that center of the string to a pivot, and then we oscillate that pivot along the vertical direction. We are going to have collision with increasing amplitude, and we should investigate this phenomenon. So this is an overview of what we're going to talk about today. At first, we're going to have our phenomenon demonstration, then we are going to get to our preliminaries, which are about key parameters and resonance. After that, we are going to have a theoretical model, which is based on period equations, then our experiment results, and at the end part, we're going to have our theory versus experiment. So this is a demonstration of our experiments. As you can see, we are oscillating the pivot along the vertical direction, and then we are going to have a maximum distance between the balls, and then we are going to come back and collide back and forth. So let's get to our preliminaries. In this slide, I want to talk about the key parameters which are affecting this phenomenon. For the string, we have material and the length of the string, which is a very important parameter. For the pivot, we have the period and the oscillation range, which is the range that we oscillate the pivot in. And for the ball, we have the mass and the materials of the balls, which also play a key role as well. So the length of the pendulum, which is a key parameter, has the effect on the period and the frequency of our oscillations. As we know, the more length we are going to have, the more it's going to take to have our each period. And the next parameter that I'm going to talk about is the mass that the balls have. And we know the heavier the balls are, we are going to retain more momentum and energy during our collisions. So the motion is going to continue for longer. And the lighter balls we are going to have, we are going to lose energy faster, and the motion is going to go down quicker. Now let's talk about resonance. So what is resonance? Resonance is when the driving frequency of our oscillatory system is matching our natural frequency, which means the frequency that we oscillate the pivot with our hands, if it matches the natural frequency of our system, which is double pendulum system, and the natural frequency of pendulums can be calculated by this equation as you can see here. And then if a resonance occurs, we are going to have our collisions with increasing amplitude, which the face of the equation is stating. Okay, so for a brief phenomenon explanation, we know that at first we are going to have a vertical oscillation, then resonance will occur, and then we are going to have our collision with increasing amplitude. And then if we don't inject any external force into our system, the system will damp and the motion is going to eventually stop. So now let's get to our theoretical model. So for calculating the period of a single pendulum, we can use this formula, which in most cases are for angles in pendulums less than 15 degrees, which we use this equation. And then for our modeling, which it is in Lotto and it's a double pendulum system, the motion of the pendulum is going to be divided in half. Because of that, the period is going to be also divided in half, and if we divide our equation by 2, we are going to get rid of the 2 multiplier of our equation. And this formula also is in most cases for angles less than 15 degrees. So now, in cases that we have larger angles, we can use this equation for a simple pendulum. And again, if we have our Lotto system, which is a double pendulum system, we will divide our equation by 2 again to get to the period that each collision has. When we are oscillating the pivot with our hands, we are introducing an extra acceleration into our system, and that acceleration is going to be added by the gravitational acceleration, and that is going to give the effective acceleration that we have in the system. And in here, A is the vertical acceleration we are dealing with the pivot, and we consider A as a constant in our theory for simplification. So now let's talk about oscillation range. Oscillation range is the range that we oscillate our pivot in Lotto, which is equal to this equation as you can see. And then at the end part, we are going to get to that equation which states that the period that we are going to have for each collision is going to be equal to the square root of 2d over a bar, which is our average acceleration have kinetic energy dissipation in three main mechanisms in this phenomenon. At first, it's going to be caused by elasticity of the walls mostly, and then we're going to have the air drag, and the last part is the minimum dissipation, which is in this case sound. So the energy loss that is caused by elastic deformation, and overall the energy, the kinetic energy that we're retaining in our system can be calculated by the coefficient of restitution, which compares the velocity that we have after each collision with the collision beforehand with the velocity that we have before the collision, which shows how much of the kinetic energy is going to retain in our system. Next up, we are going to have the air drag, which kinetic energy is going to turn to thermal energy, and it's going to be thermal energy waste, and the drag force can be calculated by this equation, which we also calculated the air drag that we had in our experiments as well. So in our modeling, for calculating the kinetic energy loss, we model the energy that is getting wasted in our collisions by the work we are doing in our hands. So we modeled it in this way that whenever we are introducing the extra energy with our hands, with the work we are doing, we are adding and making up the kinetic energy waste that we have, and then we calculated the total energy that we have in our system, and then as we got the ratio of it, we can calculate the wasted kinetic energy that we had in our each collision, which was around 57%. So now let's get to the data that we got from our theory. This is the data and the graph that we have from the different lengths of the pendulum. This is how it affects the period of each collision based on this theoretical equation that we had. And next up we had our acceleration. You see how much the acceleration and how the vertical acceleration in our hands will affect the period that we are having in each collision. And during this theoretical approach, we made the L to be constant, so it will not have a different effect. So next up for our experiments, this is our experiment setup. We use different locos with different lengths for our experiments. We had a fixed iPhone camera to record the slow motion videos, which were 60 frames per second, and then we used an online tracker to track things like the angle that we had in our collisions for our equation and the vertical acceleration that we were having in each collision. So this is the data that we got from our experiments, and these are analysis. We tested 5 different lengths, and in each point we have 5 tests, which each point is an average of that 5 tests that we had, and that is the trend line that shows the trend that we had was very similar to the theoretical data that we got, which verifies our theory. In here again we got the data that we got from our experiments for the vertical acceleration, and as you can see again, the effects were pretty similar to the data that we got from our theory, and it shows the more vertical acceleration we are having, the less period we are going to have in each collision. So overall, for our theory versus experiment, as you can see, we are comparing the results that we got from our theory and the data that we got from our experiments. And it shows and it confirms the theory that we have, and it shows the more length we have in our pendulums and locomotive, the more it will take for our collisions to be completed, and again, the more acceleration we are having, the less complex we will take and the less period we will have. So now let's get to our conclusion. So for our theoretical approach, the main thing that we got from our theory was this formula, which also included the accelerations and the division by 2, again because of the limited motion and the half motion we are having in the and it's important to note that the theta 0 here is the maximum angle that we are having in our collisions, and it should be considered as body. This equation also has some more terms which acceleration had the opposite effect, and it showed that our experiments also verified our theory is going to be accurate. So, and at the end part, we had a comparison in theory versus experiment, which were these two graphs. As you can see, again, it showed that it verified our theory, and shows that it does not have problems and the calculations were accurate. These were the references that we used for our presentation, and thank